Doing every challenge question, part 50, the big 5-0. This is Core Pure 2, chapter 6, which is the hyperbolic function chapter. I'll say on the record here that a guy called Dr. Trevor Bezet, I hope I've remembered his name right, has made an incredible video on hyperbolic functions that everybody should definitely watch. He made it semi recently. You should be able to find it. Anyway, to start with, we're going to sketch these graphs here. I've taken advantage of the fact that the book tells me what cosh looks like. It looks like this. And so now I'm going to use that to just draw 1 over cosh. Now, if I'm not allowed to use that, I could have drawn this on my own, because I know cosh is defined to be this, and this is just the graph e to the x, which is like this, plus e to the minus x, which is this, added together, so they add together to make a U shape, because you just add up where they are at any point, and then when you divide by 2, you still have a U shape. So yeah, that's fine. And then 1 over that, well, 1 over 1, just do it bit by bit. 1 over 1 is 1. 1 over something bigger than 1 is less than 1. 1 over something bigger still is less still, and then less and less and less. 1 over a really, really big number is basically 0. It's going to pan down to 0 here. And then likewise, same thing on the other side, and you end up with a graph that looks a bit like this. Next one is cosec, which is, of course, 1 over sinh. Book tells me sinh looks like this. Again, I could have figured this out by the definition by doing e to the x and then taking away the backwards one and then dividing by 2. I'd end up with an S shape. It wouldn't be too hard to get. But in any case, so let's do 1 over this. 1 over 0 doesn't exist, so it doesn't exist here. 1 over a very small number is a very big number. 1 over a slightly bigger number is a slightly smaller number, and so on. So you're going to get smaller and smaller and smaller, doing 1 over bigger and bigger things. And likewise over here, 1 over a very small negative number is a very big negative number, and you're going to track down like this, and you're going to end up with a graph that looks very much like the 1 over x graph, I guess, something a bit like that. Good, so that's cosec, and then coth. So that's 1 over tanch. Now, tanch, the book doesn't tell me what that looks like, so I will figure it out real quick. It's sinh over cosh, which is this over this. The 2's cancel, the divide by 2's. Now, there's a few things I can say about this. Firstly, if x is 0, this is 1 minus 1, which is 0 on top, and so therefore tan h is 0 at 0. So it goes through the origin. If x is like a really, really big number as it tends towards infinity, you get e to the infinity minus nothing over e to the infinity plus nothing, and that's just 1. And likewise, when it's negative infinity, it's the same thing, because these are the ones that go to infinity, and then you have a minus and a plus, and it just goes to minus 1. The last thing I'll say is that these numbers are always positive. E to the power something is always positive no matter what, which means this numerator is always less than this denominator, which means that this graph never gets bigger than 1, and it also never gets less than minus 1. So it's going to track up to an asymptote at plus 1 and minus 1. But it's never, and it's going to go through the origin, but it's never going to go above 1 or minus 1, which means it must look like this, basically. This is pretty much the only thing that it can do. And then we'll just do 1 over tanch. 1 over 0 doesn't exist. 1 over a small number is a big number. 1 over a slightly bigger number is a smaller number, and it tracks down like this, like the previous ones did. And then likewise on the other side, it's going to track down like this. And you end up with a sort of similar graph to sinh, or sorry, to cosec. But it has this big gap in the middle between 1 and minus 1. It looks a bit like this here. Find the first 3 non-zero terms of sec of x. So we're going to use the Taylor series evaluated at 0. To do this, so let's call f of x sec of x. Now remember, that's 1 over cosh, which is cosh to the minus 1, which is that e to the x plus e to the minus x over 2 flipped over. So it ends up being this here. And now this is the easiest way to evaluate f of 0, because you just put zeros in here and you get 1 plus 1. 2 over 2 is 1. So that's good. Like I said, this is also cosh x to the power minus 1. So to differentiate sec, I could differentiate this, which means bringing the minus 1 down to make a minus. The minus 1 turns into a minus 2, and then the derivative of cosh is sinh, so that's f dashed of x. Now sinh, remember, is e to the x minus e to the minus x over 2. So when I evaluate this as 0, put in zeros in here, you get 1 minus 1, which is 0, and so this is 0, and so the entire thing goes away, which is actually annoying, because that means I'm going to have to differentiate more times to get the first 3 non-zero terms. But okay, that's fine. Let's differentiate this now. Now, I'm actually going to simplify this a little bit, because this is sinh over cosh squared, and that's sinh over cosh cosh. Sinh over cosh is tanch, so that's tanch over cosh, which is tanch sec with the minus in front. So I think I can say that's all of that. Now I can derive this. Now, what I want to notice here at first, though, is that now I have a shortcut. To derive sec, it's just minus tanch sec. So when I derive this here, I'm going to use product rule. Now tanch derives to sec squared, because for the same reason tan derives to sec squared. So if I use product rule, this one derives to sec squared, which just makes this a minus sec cubed. And then when you derive this one, you get a sech, you get minus tanh sech, which combines with the tanh to make tanh squared sech, and then the minuses cancel, and you end up with this here. So I actually did this one first, and then derived this for this here. Now evaluate this at 0. Tanh of 0 is 0. We actually saw the graph earlier, so that would be one explanation as to why, but also it's because tanh is sine over cosh, and sine is 0, so it's just 0 over something. So this is 0, so when you put in 0, all that matters is this one, and we've already seen that sech turns into 1, 1 cubed is just 1, so that makes a minus 1 here, as that bit there. Now we need to derive again, so I'll just leave that information there somewhere. We do need to derive this again, so okay, let's derive this one via product rule. So tanh squared, you can write that as I just said it, tanh squared here. Bring the 2 down, lower the power down to a 1, that makes 2 tanh, and then the derivative of tanh is sech squared, so that turns into a sech cubed there. And then you derive this one, which we saw becomes a minus tanh sech, so that becomes a minus tanh sech, increase the tanh to a 3, put a minus here, and tag a sech from the end. And then sech cubed, that's sech brackets cubed, maybe put the 3 down at the front, turn it into a 2, but then the derivative of sech is minus tanh sech, so it increases it back up to a 3 again, changes this to a plus, and you have a tanh on the end as well. So that's that done. Evaluate that at 0, and the tanches in every single term mean that it's just going to be 0. So that one, as much as it was effort to find, doesn't actually matter. At this point, I actually noticed that these two things can go together to make this, and now deriving this one more time is going to be a bit more easy. Derive tanh for sech squared, so that makes this into a 5. Derive this for bring the 3 down to make a 15, turn this into a 2, but then you times by minus tanh sech to turn it back into a 3 again, turn that into a 2 and make a minus sign, and that's going to be this term via product rule. And then this one via product rule, tanh cubed derives to 3 tanh squared sech squared, so that's going to be the 3, and then the sech squared turns into a sech cubed here. So that's all that done. And then derive this one for a minus tanh sech to turn this into a plus, increase that by 1, and then have the sech there. Evaluate this at 0, and these two things, in fact, all of those go away. We end up with 5 times 1, which is 5, and that'll be that good to go. Now we can use the Taylor series. We have 1 as the first term, 0x as the second term, minus 1x squared over 2 as the third term, 0 as the next term, and then 5 over 4 factorial x to the 4 as the fourth term. That all cancels down a little bit and goes away to make this here, which will be our correct expansion. Some integrals to do, which is always nice. So dx is equal to cosh theta d theta. And this actually works out quite nicely, quite quickly. You put that information in to get this. So I'm just replacing the x's with 1 plus sine theta, like this. And now if you do some expanding out, you get this. A lot of stuff cancels here, which is very kind of it. And you make this here. Now sine squared plus 1 is just cosh squared, which is really nice because cosh squared to the power 3 over 2 is just cosh to the power 3, I believe. And then that cancels a little bit with this to give you 1 over cosh squared, which is otherwise written as sech squared. But we saw previously how tanh derives to sech squared, so therefore sech squared integrates straight to tanh, and you end up with tanh theta plus 3. Now that's not what they asked you to get, so we're going to need to put the thetas back in, or the x's back in, to replace for theta. Now tanh is sine over cosh, as we have seen before. But of course, sine is just x minus 1, so that replaces immediately. Cosh is a bit more difficult to deal with. Let's take away the 1. So that's where this is going to get replaced from, to make an x minus 1. But then here, to make a cosh, let's square both sides to get this, expand that out properly when you square it. As we saw before, if we add 1, if we take away, well, we could have added 1 in. But anyway, sine squared is cosh squared minus 1. And now I'm going to add the 1 in to get this, and then I can square root. There's no plus minus because cosh is always positive, as we saw from the graph earlier. So this just replaces in there, and we end up with exactly what they wanted us to get. And that is that quite fun integral done and dusted. Another one, so I had no idea what to do here. So I just did the most obvious substitution possible, which to me is just u equals x squared. And it turns out it works marvelously. So du is 2x dx. You can replace dx with du over 2x and replace this x squared with a u. These x's cancel, which is very kind of them. The half comes out to the outside here, and we're just integrating cosh squared. Now we can use a few of these relations. They're in the formula book here. This one looks like the most helpful one. So I think I can write this as, well, sine is is cosh squared minus 1. So this makes this into 2 cosh squared minus 1. Now, if I add the 1 and divide by 2, I could get this. But when I divide by 2, I'm just going to put an extra 2 down here, and I'll just end up with this here. And this is very easy for me to integrate. I'll just integrate it in the usual way and put the u's back in, of course, for x squareds, and I should end up with my answer just there. I guess I should have put a plus c, but I don't really care. B then, I didn't know what to do, so I did the same substitution, and it turns out it worked marvelously. So the same substitution, you get this here. The x's cancel again, which is super nice. Then this turns into a sec squared. We've seen this before. Tanh derives to sec squared, so sec squared integrates to tanh. And then you put the x back in for you. I guess I needed a plus c here. I forgot. Who cares? Last one here is, this is the graph y equals sec of x. Integrate between infinity and minus infinity. So we've seen that sec squared is a very easy integral to do. Sec is not as easy because we don't just have the known derivative or antiderivative, I guess. So this ends up being a touch harder. I had to think this through a little bit. But what I decided to do was say, well, sec is just 1 over cosh. And cosh is, or 1 over cosh will be defined to be this thing here. So I thought, well, maybe there's a better way of integrating it by just considering it as exponentials instead. Now, this doesn't seem that easy, but if I times top and bottom by e to the x, I'll get this. And this feels like I've made some progress because it sort of feels to me, what I was aiming for here at the time was to get some kind of log to happen, because this is kind of like the derivative of this, except it's not. And what actually happens is actually slightly nicer. If you make a quick substitution like u equals e to the x, which I only did just to help me see this a bit easier, because it's like u and u squared, and again, that was where I was trying to get the log involved. Of course, when you differentiate this, it messes it a little bit up. So du is e to the x dx. But it actually doesn't mess it up, because it actually means that dx is du over e to the x, which cancels with this e to the x. And you end up with this integral here. Notice how the limits have changed, because if x is infinity, then u is still infinity. But if x is minus infinity, e to the minus infinity is 0, so u is 0. So that's where these limits have changed here. These cancel, and this integral is actually just a known integral, so I really lucked out here. This is just arctan. It's in the formula book, but this is just arctan. The formula book has an a squared here, but that's fine. A is just 1 then, and you get this here. Arctan of infinity, well, you're asking for what tan of what gets you infinity? Well, that's pi over 2. And arctan of 0 is just 0. And then 2 times pi over 2 is just pi as required. Nice little question.